Hi everyone, today we will look at the architectural diagram illustrating the real-time event processing system using Kafka, Redis, Async Writer, and PostgreSQL. This diagram illustrates a high-performance real-time event processing architecture designed for logistics tracking systems. It uses Kafka for scalable event ingestion, Redis as a write-ahead buffer to handle peak loads, and an asynchronous writer service to persist events efficiently into PostgreSQL. The architecture ensures low latency, high throughput, and resilience, ideal for mission-critical systems requiring accurate and timely data delivery. The system's purpose is real-time event handling. The core components are Kafka, Redis, and Async writers, and the design goal is scalability and performance. Here we have the event source like a GPS tracker, a delivery app. These are the systems that generate real-time logistics events such as shipment updates, GPS coordinates, or status changes. Events are typically JSON payloads sent through REST or MQTT to the system. Then we have the ingestion layer, which is Apache Kafka. Kafka is a central message broker. It ingests high volumes of events and stores them in a durable, partitioned, replicated log. Kafka enables decoupling between producers, event sources, and consumers, our processing services. Redis is a write-ahead buffer. Redis is used as a fast in-memory buffer before database writes, helps absorb spikes in traffic, and allows batching of events. Acts as a short-term queue for transient persistence and resilience. Then we have the async writer service. This service fetches events from Redis and Kafka, batches them, and writes them asynchronously to the database. It ensures ordering within partitions, retries on failure, and scales horizontally. Then we have the PostgreSQL, which is the primary data source, the final destination for enriched, cleaned, validated event data. Events are stored with strong consistency and made available for querying by downstream systems. Then we have event consumers, which are downstream services. These are analytics, alerting engines, or user-facing APIs that consume persisted event data. They rely on timely and accurate delivery of data into the database. Let's talk about event ingestion. Logistics systems or mobile clients send event payloads. Examples: shipment location update to a Kafka topic. Each topic may represent a different event type. Example: shipment.gps or shipment.status. Kafka partitions the topic to allow parallel processing. Step 2. Kafka to Redis buffer, optional for hot events. Events are optionally pushed to Redis for high priority use cases. Example: real-time UI updates. Redis acts as a fast, short-term buffer and stores event batches grouped by shipment ID or time window. This reduces pressure on the database and helps prevent spikes during peak loads. Step 3. Kafka to async writer, code path. Kafka to async writer. The async writer service subscribes to Kafka topics and processes records in batches. It deduplicates orders by event timestamp or version and enriches events before storing them. This service supports backpressure handling and scaling via multiple consumer instances. Step 4. Redis to async writer, fast lane writes. For events stored in Redis, the async writer periodically polls or listens for changes. It merges Redis buffered events into the same pipeline as Kafka derived ones to maintain order. Ensures Redis is used for resilience, not as a permanent queue. Step 5. Async writer to PostgreSQL. The writer batches events and inserts them asynchronously into the appropriate table. Example: shipment events. PostgreSQL transactions ensure data consistency and rollback on failure. Write performance is optimized using bulk inserts, upserts, and partition tables. Step 6. PostgreSQL to event consumers, such as analytics, APIs, and alerts. Downstream services query the database via APIs or event triggers. Alerts are triggered when specific event patterns are detected. Example: shipment struck. ETL jobs or materialized views may be used for dashboard reporting. System benefits. Latency reduced from 2 seconds to 300 milliseconds during peak load. Scalability. Kafka and Redis handle spikes gracefully. Reliability. Asynchronous retries and DLQ ensure no data loss. Observability. Traces and metrics via open telemetry. Modularity. Easy to plug in new consumers or processors. Optional enhancements: dead letter queue, DLQ, store failed events with reasons for later retry. Schema registry, manage event versioning safely. Monitoring, Prometheus for metrics, Grafana for dashboards. Flow control, back pressure via Kafka, consumer lag detection. Security, use TLX and signed messages for secure transport.